Welcome to Section 3 of Chapter 4, where we will be learning to distinguish among atoms. What is it that makes up an atom? There are three basic subatomic particles. There are protons, which have a positive charge, neutrons that are neutral, and electrons with a negative charge. Where are these particles found? If you look in the diagram in the lower right, you can see that protons and neutrons are found in the nucleus. Electrons are found somewhere around the nucleus. Just how big are these subatomic particles? The mass of a proton is very small. It's that number there, which is 1.7 times 10 to the negative 24 of a single gram. So it's extremely small. To work with a nicer number, we're not going to work with grams when we talk about atoms. We need a different unit, so we're going to use the atomic mass unit. That's abbreviated AMU. This unit was defined to be 1/12 of the mass of a carbon-12 atom. Now this is a carbon atom that has 6 protons and 6 neutrons. That's why it's called carbon-12. Since protons and neutrons have about the same mass, each one is said to have a mass of about 1 atomic mass unit. Electrons, however, are much smaller, about 1,840 times smaller than a proton, or you could think of it as 1/1840th of the size of a proton. Since they're so much less massive than protons and neutrons, they don't have much of an effect upon the mass of an atom. Most of the atom's mass will be found in that tightly packed, very dense nucleus that we see in this diagram. The way we determine which element it is we have to look at what's inside of an atom of that element. All atoms contain protons and electrons, and almost all of them also contain neutrons. There are over 110 different elements. What makes an atom of an element different from an atom of any other element is the number of protons. That's why we call the number of protons the atomic number. It's the atomic number, or the number of protons, that determines what element it is. As long as you have an atom of an element, then the number of protons will be the same as the number of electrons, or number of P will equal number of E. That means that all atoms are neutral. They have no charge, since the number of positively charged protons is equivalent to the number of negatively charged electrons. What does a hydrogen atom look like? A normal hydrogen atom actually has a nucleus consisting of just one proton, and a single electron is moving around that nucleus. Since it has one proton, hydrogen's atomic number is 1. On the right, we can see a variety of different representations of hydrogen. A normal helium atom has 2 protons in its nucleus, as do all helium atoms, but it usually has then 2 neutrons as well, and 2 electrons move around this nucleus since it's a helium atom. Equal numbers of protons and electrons. Helium's atomic number is 2. So what is the purpose of the neutrons? Why do you need those 2 neutrons in there? Think about it. If you have 2 positively charged protons next to each other, what are they going to do? 2 positive charges right next to each other, you should know, would repel. Those neutrons help to separate the protons. In so doing, it keeps the protons from repelling each other as much due to a strong force that holds them together next to the neutrons. So if there were no neutrons in the nucleus, the 2 protons in your helium nucleus would be right next to each other. They would repel, as I've said. So the neutrons are there to reduce the repulsion of the protons so that they can exist within the same nucleus and not make the nucleus unstable due to repulsion of like charges. Some hydrogen atoms do contain neutrons. Although I pictured it earlier with 1 proton surrounded by 1 electron, some hydrogen atoms actually have 1 neutron in it, and it's referred to then as heavy hydrogen. If you think about it, you know that the mass of a normal hydrogen atom is going to be 1 atomic mass unit, because it has just the 1 proton. Whereas the mass of this heavier form has the mass of the proton plus the mass of the neutron, giving it twice as much mass. Hence, we call it heavy hydrogen. Another term for it is deuterium. So that means that there's more than 1 type of hydrogen atom. Actually, there are 3. These differ only in the number of neutrons they contain. But if we think back to our story of the development of the theory of an atom, we know that John Dalton said that atoms of the same element are all identical. Now we know he didn't have everything right. John Dalton was wrong about that fact. Now we're ready to talk about isotopes of an element. When atoms share the same number of protons, meaning they have the same identity as an element, but they differ in the number of neutrons, we call them isotopes of the same element. They're still the same element because the number of protons is what determines that, but some are heavier and some are lighter. Isotopes of the same element have the same atomic number, same number of protons. They do have different atomic masses, however. The one with more neutrons will be heavier, such as our hydrogen and heavy hydrogen or deuterium pictured here. As atoms get bigger, they have more protons. They need more neutrons to help make the nucleus stable because more protons will have more repulsion. You need more neutrons in there to help separate those protons. We want to make that nucleus stable. The problem is it's also possible to get too many neutrons in the nucleus, too much of a good thing. That will also cause the atom to be unstable. You don't want to have too many neutrons in there either. So what happens to an unstable atom? Whether it's unstable because it has too few neutrons, or unstable because it has too many, or unstable for other reasons. What does it mean to be unstable? What are the implications? An unstable atom has a nucleus that will change over time. You heard me right, the nucleus changes over time. They will spontaneously emit subatomic particles, changing what the nucleus is made out of, which means it can change the identity of the atom. When atoms give off subatomic particles, they also give off large amounts of energy. That's what we call being radioactive. You can tell by looking at this poor fellow that he understands radiation pretty well. Being exposed to a radioactive element, that high energy given off, can disrupt cellular membranes. Radioactive elements are dangerous to be around in large amounts because, as you can see, radioactivity is damaging to human cells. It can actually affect your DNA and cause defects in development, such as what we see here in this frog. In the early development of the egg, that egg was probably exposed to some form of radiation which caused damage to the DNA. As you can see in this diagram, if the radiation affects a sequence of base pairs in DNA, then it can cause radical changes in how those instructions are followed. While some isotopes are stable and can survive indefinitely, others are unstable. Unstable isotopes undergo what's called radioactive decay, trying to reach a more stable form. Now, often that's by becoming other elements. This is not a physical change and it's not a chemical change. It actually falls into a new category of changes called a nuclear change. And as mentioned, it can change the identity of the atom, which neither physical nor chemical changes can do. As you look at this diagram, you can see that radiation is emitted as a particle is ejected from the nucleus of the radioactive atom, and high energy waves are given off. Now we need to have a way to tell isotopes apart. Since isotopes of an element differ only in the number of neutrons, we can use that fact to help identify them. What we actually use is something known as the mass number. Those are used to tell the different isotopes apart. Different numbers of neutrons will make the nucleus have a different mass. The way we calculate the mass number is to find the number of protons and neutrons and add those together. That will give us the mass number. As we can see here, we have two forms of carbon. The atomic number is written down below and the mass number is written up above. The one on the left has a mass number of 12 and an atomic number of 6. So it has 6 protons, and in this case it must also have 6 neutrons for those to add together to become 12. In the right side we have carbon with 14 for its mass number and an atomic number of 6 still. So it still has its 6 protons, it's still carbon, but it must have more neutrons because its mass number is 14. It must have 8 neutrons. 6 plus 8 would give us the 14. These are all helium isotopes shown here. Each of them has 2 protons. That's why we know they're helium. But they have different numbers of neutrons. Those neutrons are pictured in yellow. As I count the numbers in their nucleus, I see that their mass numbers are 5, 6, 7, and 8, respectively. So how do we name isotopes? the way that we name them is to give the name of the element, then we follow it with a hyphen, and then the mass number. So, since these had mass numbers of 5, 6, 7, and 8, these isotopes would be called helium-5, helium-6, helium-7, and helium-8. Let's try to name the isotopes shown below. We can do that either by looking at the pictures or looking at the element symbol. You should recall that on the lower left, they show the atomic number. On the upper left, they show the mass number. So we can look at this, and Li stands for lithium. So looking at those symbols, we know that these are lithium-6, lithium-7, and lithium-8. We can also tell that from the pictures. If they didn't give us those symbols, we would have to look and see that each one of these does contain 3 protons, which means that each one of them is lithium. The first one contains 3 protons plus 3 neutrons to make a mass number of 6, so this is lithium-6. The next one has 3 protons and 4 neutrons, so it's lithium-7, and the last one has 3 and 5, which makes a total of 8, so it's lithium-8. We will be doing this example in class, and we're going to stop here at this point. We'll do part 2 on another day.